Assalamualaikum warahmatullahi wabarakatuh, and a very good day to my fellow lecturers and judges. My name is Umairatul Afiqah Binti Nazri, and I will be presenting my final year project, which is called Computational Fluid Dynamics Analysis of Evaporative Passive Porous Wall. So we'll look at the background study. So based on the Department of Statistics in Malaysia, the increasing population in Malaysia has led to high demands of cooling appliances for thermal comfort every year. So building sectors are among the highest energy consumers in the world and has significantly shown great impact to the environment. According to Putra, almost 30% of energy consumption in every household per year comes from cooling devices such as ceiling fans and air conditioners. Problem statement. Problem arises when the huge demand of cooling systems in buildings causes an increase in energy consumption and contributes more to the environmental hot climate. This will directly affect the thermal comfort of occupants. So the objectives of this project is to reduce the indoor air temperature of buildings by harvesting rainwater for porous cooling walls. The second objective is to increase the cooling efficiency between benchmark design and the new wetted porous cooling wall. Next, we'll further discuss on the methodology of this project. So the first is geometry drawing, which consists of two parts, which is the airflow zone and wetted porous zone. So airflow zone is where the air from outside enters into the building, and wetted porous zone is where the cooling wall is. And here, the table is where all the values for the parameters of the geometry. Next is the surface mesh. So the surface mesh method is triangular because both zone is in fluid condition, and the element size for this is 25,191 elements, and grid divergence test is conducted to obtain the most accurate results from the analysis. So next is the solution model for the simulation. So the viscosity is laminar flow, the energy equation is enabled because there's heat transfer present, and the porous zone and the airflow zone is in fluid medium. Porous zone is set to 0.38, and the inlet air with the velocity of 0.5 meter per second, inlet water with the mass flow of 0.011 kilogram per second. The interfaces are enabled between the airflow and the porous zone, and the scheme is in simple algorithm, and the pressure, momentum, and energy, and also the gradient is set to default. Next, we will further discuss the validation results. So here is the temperature contour for the simulation of validation. And here is the graph we obtained comparing the benchmark result with the previous study. And we obtained the percentage area of 27.23%, which is quite huge, but the reduction profile matched closely with the result in the previous journal. So this shows that the proposed evaporative cooling wall produces a significant effect on the cooling characteristics. So after the validation, we set a new parameter on the cooling wall, which is the thickness of wet porous wall, and 3 thickness is set, which is 0.01 meter, 0.02, and 0.03 meter. And from the simulation, we obtain that as the thickness of the porous wall increases, the temperature decreases. After the outlet temperature was obtained, we calculate the cooling efficiency of the system. So the wet bulb temperature was obtained in the previous journal, which is 21.85 degrees Celsius, and we obtained that the thickness of porous wall with 0.03 meters performs better cooling efficiency of 85.93%, and this shows an improvement of approximately 34% increase from the benchmark design. The second parameter change was the porosity of wet porous wall. So we changed into 3 different values, which is 0.4, 0.45, and 0.5. So this is the graph obtained for the porosity of wall versus the temperature. And we can see here that there is a slight decrease of temperature as the porosity increases. After the outlet temperature was obtained, we calculated the cooling efficiency, and it was calculated that the cooling efficiency increases as the porosity of wetted porous wall increases. But the difference are quite small. The difference between porosity value of 0.4 to 0.5 increases by approximately 3% only. So based on this analysis, the cooling efficiency increases slightly only as the porosity of wetted porous wall increases. Next, we will discuss on the impact of ceramic porous wall. In terms of health, it is free from formaldehyde and volatile organic compound, which is dangerous for occupants. Next is safety, which is ceramic wall is non-flammable material, which means it doesn't catch fire easily. And in terms of environment, it can reduce usage of electrical energy in buildings. And in society, it can help people in rural areas that have limited access of electrical supplies or even cooling appliances. In conclusion, the defined problem statement has been solved and the project has met the objectives with the details. By harvesting rainwater for porous cooling walls, the airflow temperature of 35 degrees Celsius was reduced to 28.23 degrees Celsius, which have a temperature difference of 6.77 degrees Celsius. And comparing the new results with the benchmark design, wetted passive evaporative porous wall with thickness of 0.03 meters is able to reduce a cooling efficiency of 51.48% to 85.93%. So that is it from me. Thank you.